So let's start with our webinar on DeepQ network. So why do we need to use a deep neural network in the first place? Uh, as you might have seen in the previous part of this annual degree that to solve these environments, you didn't use a neural network. You just use a simple program, simple uh, code with some policy that decides the policy and it used to execute and solve the environments. So why do we need to use a neural network in the first place? So in the previous examples, in the previous environments that you worked on, the state spaces were discrete. So, so as you can see in this example, the grid world example, there were limited number of states and even the actions were limited number of actions and they were discrete, they were not continuous. So, so it was possible to express this Q table, express this action value function in the form of a table. We used to uh, enter these action values in the Q table and then run many policies and then used to come up with an action value function. So it was possible to use a Q table for that. Similarly, in this example, um, there are finite number of states and the state spaces are discrete. It's either 0 or state 1 or 2 or 3 or 4. There is nothing in between uh, this in these two states. It's either 0 state or 1 state or all right. Same goes for actions. It's either left action, right action, or stay action. There is no action in between left and right that that was possible. So this could be expressed in the form of a table, and a table could be used to compute the action value function in this case. But if we have an environment or a task that has continuous state spaces, for example, you might have seen this cart pole environment in one of the quizzes. Uh, and in this case, the state, one state, is defined by these four variables that you see here. And each of these variables takes a value in between a range. So for this, it's minus 2.4 to plus 2.4. And for this, it's infinite and so on and so on. The value for each of these variables comes in a range. And one state will be a combination of the four values of these variables. So in case for one state, for example, one of the values is minus 2.41, and if you use the same value for each, okay, some random value but same value for each of these states, that will be one state. So each of these variables, so that will be one state. Then next state could be minus 2.411. So again, keeping the same values, you will get another state. And next could be another small increment, and those small increments could be infinite, and that's why there are infinite values possible for just one variable, and same goes for all these variables. So in this case, the combinations of all these will be infinite, so it is not possible to uh, express those infinite states into a table form because we want to compute action value function. uh, yeah, and in this case, so this is just an example, this is not for the card pool, but we saw these uh, state variables previously, but the actions here in this case are discrete. It's either zero action or one action, either left or right. There is nothing in between. But there are environments, and even in real life, if you are solving real life problems, even the action spaces can be continuous. So the number of actions can be infinite given a state. So it becomes even more difficult. So let's see. So this is a pendulum example. This is a pendulum environment from OpenAI Gym. Again, the values for each of the state variable lies in the range. So there will be infinite state spaces, and even the action lies in a range. So the amount of force can be any number between these two ranges. So it becomes very, very difficult or even impossible to express these number of states and actions in a Q table. So for this reason, we need to use a neural network. Uh, there is one more way of dealing with continuous state spaces, and that is discretization. So this method is covered in more detail in our classroom in one of the lessons on RL in continuous spaces. So basic point of that discretization is that you divide this continuous state space into small ranges, and then you discretize it. So the state spaces become finite because the ranges will be finite. Uh, but even a better way of solving this problem is to use a function approximator. So neural network is a very complicated function approximator. By function approximator, I mean is that, let's say this blue curve is the optimal action value function. So given a state and action, each point on this blue curve gives out a action value corresponding to one of the state and action pair. And so we want to uh, approximate this action value function. We want to come up with a way such that do this uh, I can do this manually. So neural network is one of those ways to approximate this function. So you can see this yellow curve. It's not exactly coinciding or overlapping the blue curve, the optimal action value curve, but it's kind of around it, right? So that's what a neural network does. When you train the neural network, it will create an action value function that is very good approximation of the optimal action value function, right? So how do you visualize this? So in this case, the state space is continuous, so there will be infinite number of states. So again, I would like to avoid this confusion that there are four variables defining one state, but the combinations of these four are infinite. That's why I'm saying that the number of states possible here are infinite. Okay, so and in this case, the action space is finite, and so this is how the neural network will work, that you input a state which is a combination of these four variables in this case, in this example, and the final node will give out two action values because there are two actions. So it will give out two action values, and looking at those action values, you decide which action you want to take, whether you have a greedy policy or you have a random policy or whatever policy you have. Based on the action values generated by this network, you determine your action. So this network will take a state and give out action values corresponding to number of actions. So that's why it's called, first of all, it's called deep. Sorry. So since we are using neural network, we call it a network, and there will be many layers in between. That's why it's deep. And what makes it a deep Q network is what we will see in the next slide. So once you have inputted this state and run through this deep network, here it's not deep because there is only one hidden layer, but uh, you will use a network with many layers, right? So it will be deep network. You run this state, uh, and it will generate two action values. And we have seen in our TD methods lesson, there is a method called Sarsa Max, which is also called Q learning. Uh, and in that method, we use the action which has higher, which has the highest, which has the maximum uh, action value. That, and it was called Q learning back then. So that's why this network is called deep Q network, because it uses a deep neural network and it decides the actions based on the max action value. It chooses the action, the best action is the one with max action value. That's why it's called a Q network. And one more thing to note is that deep Q network is a value-based method. So as you might have seen that the name of the second part is value-based methods, and the name of the third part is policy-based methods. So the difference is that in this case, in value-based methods, you first generate a, a action value function, and based on that optimal action value function, you decide your optimal policy. In policy-based methods that you will see later in your nano degree, you directly come up with optimal policy. You do not go through this intermediate step. So that's the difference. We will discuss more about policy-based methods later in the nano degree. So the point here is we first generate action value function, and based on that we determine our optimal policy. That's why it's called the value-based method. So in previous um, implementations of deep Q network, there were some issues. Um, there were some issues, and these issues were addressed by an algorithm called deep Q learning algorithm. So, so deep Q learning algorithm is an algorithm which improves the basic, very basic, naive deep Q network. And let's take a look at what these improvements are. One of the improvements is to use experience replay. Another one is to use fixed Q targets. So let's take a look in detail. So the basic DQN, uh, when previously used, you choose to train based on uh, an entire episode. Uh, One second. Sorry about that. Okay. So the previously people used to train deep Q networks based on an entire episode. They used to run uh, an environment and run it for all whole episode, and the deep Q network used to get trained assuming the whole episode is going to take place. So for example, if the first state is S0 A0, the deep Q network trains in such a way that it thinks if I have this state as the first state, I will have this state for sure later in my later in this episode. But in reality, this might not be the case. So because the environment generates states randomly. So let's discuss this in more detail. So suppose I have trained my network uh, on an entire episode, and then when I'm testing it, I get this first two, this state S0, then I will take action A0 and I will go into next state. Okay, now my trained network will take action A1, assuming S1, assuming some S1 that it experienced while training. But in reality, there could be many S1s possible given S0, A0. So when you take action A0 in state S0, the environment can present you many S1s. It doesn't have to be the same state S1 that the network experienced while training. And then in this case, thinking that it's the same state that the network experienced while training, it will give out action A1. But it will be wrong because this state S1 is not the same as the the network experienced while training. So this action won't be appropriate to this state, and so on and so on. So the network will keep making mistakes, and and yeah, it won't fulfill the task it was trained for. So the problem is that the network assumed the whole episode, and then it led to some correlations that given this state and action, I will get this exact S1, and then I will take. So the network created this correlation, and to avoid this correlation, we have this improvement called experience replay. So let's take a look at it. So how this experience replay improvement works is you have an agent and environment. Okay, so you first use epsilon greedy policy to take as many actions as possible. So you take one action, the you have first state, then you take an action, the environment gives out next state and a reward. So you collect that and store in the form of an array, of in the form of a tuple. So S0, then the action you took A0, and the reward and the state that the environment presented to you as R1 S1. Then again you take some action, and again the state gives out next reward and next the environment gives out next reward and next state. That's your second tuple, and then you store all these um, tuples together in one place, and then you will use this tuple to train your network randomly. So the first step is to just uh, sample is to just run as many steps, as many actions, and then keep collecting these state, action, reward, and next state. And you also collect done. So when you implement this in your code, you'll have to collect state, action, current state, and the action you took, the reward the environment gave you, the next state, and the done value. These three values you get from the environment. You collect them and you put them in one place in a matrix, and you stack them together. So you stack all these tuples together in a in a container. Okay, and then while training, you will sample these um, tuples randomly. So in that case, there won't be a correlation. So if you just sample one tuple and train your network, then you sample some other tuple randomly and train your network. So let's say after once you sample this and then later you sample this, so there won't be a correlation between this state and this state. So your network will learn uh, without correlation. It will take reflex based actions. If I have this state, I take this action. If I have this state, I take this action. It will learn realistically. And another plus point of using experienced replay is that you don't throw away these experiences. You store them. Previously, used to experience these episodes, and then you should just move on. You just moved on. You didn't make use of this experience properly because you are using your computing resources uh, you- to train, but you are just throwing away. You're just dumping these valuable experiences. So in this case, you are making more efficient use of your computing resources as well. That's the second plus point of using experience replay. The another improvement is a fixed Q target. So before getting into the fixed target, let's go over a typical process of training using deep Q network. Okay, so there is just one network in very basic vanilla deep Q network before any of these improvements. There is one network. You you take S0 A0 and you compute using the your current trend network parameters. You compute S0 Q of S0 A0. So you want to generate the action value given this state and this action, right? And that we'll call that as Q current. The next step is to compute S1 Q of S1 and A1. Okay, so you use the same network and you generate or you compute action value of Q of S1 and A1, and then you compute Q target, which is also called TD target in TD methods, as this. So reward plus discounted action value of next state, and then you train your current network parameters uh, by minimizing the difference between your Q target and Q current, and yeah, to reduce the loss. And so that was the basic method. You compute S0 A0 as well as, sorry, action value of S0 A0 as well as action value of S1 A1 using the same network. So that was the basic method, previous method. But that could be problematic again because you are using the same network, and the network is changing. So you're using the same network to estimate two values. You're estimating this value for sure, but that is fine because you will be adjusting your network later, right? You will be improving your network later so that your estimates get better and better. But your target value is also based on an estimate. You have to fix your target value so that it becomes a standard for Q current to follow. That's the whole point of this. But if you are training or if you are computing both values using the same network, it doesn't make sense, right? So there's a very good example in the lesson. So this is how it looks like before the improvement. You are training a horse to walk a particular path, but the target that you're giving the horse to follow is also changing with the movements of the horse, and that's why this will never work. It will always go in the wrong direction because as the horse movement change, the position of the carrot will also change, and this is how it looked in the code. You had the same weights to train to compute both the target, the TD target, as well as your current. So the improvement in this is that you fixed your Q target. So your standard that the your target or the your standard for your current network to follow is fixed, and you compute TD target using that fixed network, and then you try to improve your current network by reducing the loss between these two, and that's how your network gets better. All right, so that's why it's called fixed Q target over here, like this. Now let's take a look at the whole process of the deep Q learning algorithm. Okay, so how do you start with this? So first of all, you will collect as many experiences as possible. So you decide your batch size. Now batch size is the number of experiences you want to sample randomly to train your network. That's the batch size. So suppose your batch size is 64. So you will sample 64 uh, experience tuples randomly. So at first this, then he, this one, then somewhere else. So you will sample 64 random experiences and then use them to train your network. But before that, you should have 64 or more tuples in your replay buffer. Replay buffer is where is the container where you store all this store all these experience tuples. So so in order to sample 64, you should have 64 or more, right? So at first you will run this loop for 64 times, and then the 65th time you will sample 64 experiences. Okay, so run this, store them at first, um, and we use the epsilon greedy policy, of course. So you have some high value of epsilon at first, and as your iterations increase, your value of epsilon decays. So you're using this exploration and exploitation policy here. So at first you explore a lot, collect as many tuples as possible, and once you have enough tuples in your replay buffer, you start the training. So, and also this is up to you. The deciding this batch size is up to you. You could use 128 as the batch size, so you will train at um, train for 128, train on 128 experiences at the same time. And also the when your training starts, so in this case I said that once you have 64 tuples, you will start training the network from the 65th experience, right? But it's up to you. You can say that, okay, I will finish 100 experiences and then I will um, sample any 64 from those 100, right? So that gives it more randomness, because if you store 64 and then in the 65th, if you start your training, you will get all those 64, right? It won't be much random. So you could do that the other way. Okay. So now let's see, once we have collected enough experiences, and also um, even after you have collected these tuples and then you start training, even during the training, you excuse me, even during the training, you keep adding experiences to this tuple for each time step. So once you have, for example, 64 tuples, you take the next time step, the 65th time step, and you add that tuple as well here. So even during training, you keep adding experiences to this replay buffer. Now let's look at the training. All right. So the your local network that you will use, that is your current network or the local network, your main network that you are training, and you'll have a target network. Now these two are identical. By identical, I mean they have same architecture, same structure. The only thing is that they are two different networks, so their parameters might not be the same. They will be identical in structure. Okay, so once you have enough tuples here that you want to start sampling, uh, you will start training. So let's take one tuple here, and using your target network, you will compute QST plus 1, AT plus 1. Okay, now this one is giving you only ST plus 1. So how do you know what AT plus 1 is? So you know this based on your epsilon greedy policy. So you get ST plus 1 from here, and you determine what your next action will be given as ST plus 1 using epsilon greedy policy. Uh, and then you compute QST plus 1, AT plus 1 using the target network. and then you compute q target using rt plus 1 and this whole formula. Okay, now you have a q target, your value, ideal q target. Okay, ideal action value for q target, it will be the ideal action value for q stat, right? Once you have q target, you will compute q stat using the local network, the current parameters before training, the current version of local network will be used to compute q stat, and we will call this q expected. Okay, and then you will use PyTorch. There are libraries for minimizing the loss, and you will use that to minimize the loss between q expected and q target. And you will train your local network in order to reduce this loss. In the code, we are using mean square error loss, mean squared error loss, but you can play around with it. You can use different kinds of losses as you please. If it improves your training, or it improves your score. Okay, but the main point is to train the local network by reducing this loss. And we are always training the local network. We don't train target network, right? But we update target network. So how do you update this target network? Is by, after a few steps. So let's say after 10 steps, you will copy the 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 values of this local network 10 steps ago into target network. So the target network will be a previous version, 10 step earlier version of local network. Yeah. So after, yeah, you get the point. So the target network will be a an earlier version, depending on how many, after how many steps you update it. It will be an earlier version of your local network. But your local network will keep training and updating during each training step. Okay. Now, why are we copying local network exactly into target network? Is because we don't want too much variation in training. If we randomly select these values which are apart from this, your network will take a long time to converge, right? We don't want your network to go in a very crazy unpredicted direction. You want to keep it on track. So that's why you use a very earlier version of local network and copy it into target network, and you do that after every few steps. And in the meantime, your local network keeps training every time step. So yeah, so once you have trained your network, at first you will use, as I said, at first you will have exploration. So you will randomly select actions, and then in the end, towards the end, you will select your actions based on greedy policy, right? So that's the point of exploration versus exploitation. So when the epsilon decays a lot, in the end epsilon is very low, you will select actions based on greedy policy. So how will you select this greedy policy? Is based on the current version of the trained network. So at this point, you would have trained your network for so many iterations, and it would have experienced and explored so many different states that it is very well trained by now. It has seen a lot of states. It has seen many versions of this state, and it can be used to generate greedy actions now. So in the end, you will use your network to select actions. At first, in the beginning, you will use epsilon greedy policy, and in the end, you will use network to give your greedy policy. And how to implement this is in the sample code that is provided. And I will go through that sample code next week. It will be more clear how to. It's the simple few lines. Okay. Now, again, nothing is perfect. So even this network, this deep Q learning algorithm, which was improved, which was an improved version of the basic vanilla uh, DQN, even this can be improved, and there are improvements. So the main three improvements are using a double DQN, prioritize experience replay, and dueling DQN. Double DQN is to use two actions, sorry, use two networks to determine your action. Okay, and it's given in more detail in the lesson. Uh, let's take a look at prioritized experience replay. So this is your error, TD error, or the it's the same as this difference here. Q target minus Q current, Q expected. So that's the TD error. So you determine this error, and based on this error, you decide which tuple to sample. Right. So you want to sample, you want to give priority to those tuples who have high TD error, because your network will learn more from these tuples that have high error than the ones which have low error. Because if you keep sampling tuples which have low error, your network already is doing well on those tuples. So your network doesn't learn much from them because the error is already low, right? But you need to sample those tuples that have high error, so your network learns from them. And this is one of the way to implement this. So you can go over this. um, Priority pt was the error, and then epsilon or small value of e was added to it, so that if this is 0, then its sampling probability will be 0, so that tuple won't be sampled at all. So to avoid that, we add a small error value to it. And there is this variable a that controls how much randomness versus how much prioritized sampling you want. So this is to control the priority uh, priority factor of this sampling. And then you have to avoid some bias in this bias that is caused due to this priority sampling. There is this improvement to uh, your modification rule as well. So there is a paper about this, and the link for the paper is mentioned in the lesson. So you are most welcome to go over that. And you can also implement this in your code for the project, or even in the coding exercise, and see for yourself if it improves uh, a lot, improves your score a lot or not. It's up to you. But I encourage you to try it. Another improvement was to use dueling networks. So this is your basic DQN, and in this you just don't directly compute the Q values as here, but you compute its components first and then put them together here. And the details of this are also in a paper. You are most welcome to read those as well. So you compute the state value as well as the advantage value given all those actions. So this will compute the, the state value, and this network will compute advantage value given each state and action, and then it will be put together here. So this will amplify the action component in generating the Q value. More details are in the paper, of course. You can, and also I encourage you to implement this in your code and see for yourself if it improves your score or not. Okay, now Google DeepMind put together these three improvements and three more improvements, and then they put together these six improvements, and then they ran this algorithm, this improved algorithm on some Atari games. Right. So we discussed these three. We will see this later in the nano degree, A3C, and there are papers about these two. So you are most welcome to read this. And each of these improvements address a different issue of the DQN algorithm, the deep Q learning algorithm. So Google DeepMind put this together, and then they ran it on Atari games, and this is the result. So, and it's called Rainbow. I didn't, yeah. So it's called Rainbow because it's uh, combining this these many different improvements, and this was the result. So it gave a much higher performance as compared to these uh, improvements individually. If only individual improvements were made, or just DQN was used, basic DQN was used. Um, so if compared to those individual improvements, the combination gave a very high performance. You can see DQN is here. Prioritized DDQN is over here, and distributional DQN is here. So the max that they could do is by distributional DQN, but the Rainbow, when it combined all these the six improvements, it did very good performance. So I again encourage you to even uh, try this Rainbow improvement on your sample code for project as well as for the coding exercise, and see for yourself how much it improves. It will be a good exercise to implement those. So if you don't know how to implement, there I'm sure there are resources online on GitHub, uh, and you can find some ideas how to implement these. So that was it for this week's webinar on DQN. Next week, I will discuss the coding example in your lesson for DQN, and it will also be useful to you for your project. Some of you have worked on the projects, the navigation project, but for those who haven't, the coding exercise in DQN lesson is very useful for your project, and I encourage you to go through it, go through the code, see what each module is doing, um, and I will discuss this for sure next week. I will go into the code and explain to you. And if you have any questions about the code or the DQN lesson or any previous lessons, and even about the navigation project, uh, you can definitely ask me anytime on Slack, or direct message me on Slack. So that is it from my side. Uh, if I have any questions, I can take some questions now. Okay, there is no one. And the recording link will definitely be posted soon. Go through the lesson in the classroom and then go through this webinar. And if you still have questions, ask me anytime on Slack, and I will get back to you as soon as possible. So I will end this webinar now. See you guys next week. Bye.